Okay, in the previous unit, we've been talking about motion, we've been talking about speed, velocity. Now we are going to be talking about Newton's law. Okay, we're talking about Newton's law, Newton's first law, second law, forces and interaction, Newton's third law. But in this particular video, okay, we are going to focus on Newton's first law. And again, this is probably going to be a revision, okay, because we've been talking about Newton's first law indirectly. If you've ever heard about inertia, then you've probably been talking about Newton's first law because Newton's first law is also called the law of inertia. It's also called the law of inertia. Remember, this law was originally investigated, or inertia was originally investigated and established by Galileo. Galileo was the person that used inclined planes to establish this law. So, according to Galileo, every object will continue in a state of rest or uniform speed in a straight line unless acted upon by a non-zero force. What does that mean? What does that mean? Remember, I told you that when you placed an object on a table, right, that object has a tendency to remain on that table. It will remain on that table unless something or unless a force acts on it. The force that acts on it can be you trying to displace it, can be you trying to push it, can be wind, right, blowing that object up, can be an earthquake, okay? But there needs to be a non-zero force. Again, non-zero force means a force, a net force that is greater than zero. So unless a non-zero force act on an object, every object that is in a state of rest will want to remain in a state of rest. Or uniform speed will want to remain in a state of uniform speed. Remember, we said when an object is in equilibrium, equilibrium means that that object can either be in a state of in a state of constant speed or it is at rest. So this is the same kind of scenario. Okay, so if there's no net force acting on an object, that object will want to remain in a state where it is. So if it is moving, it will want to remain in that state of constant speed, or if it is at rest, it will want to remain in a state of rest. Now let's check this. You have a sheet of paper that can be quickly withdrawn from under a soft drink can without the can toppling because A. Gravity pulls harder on the can than on the paper. The can has weight. The can has inertia. None of the above. A sheet of paper can quickly be drawn, right, under a soft drink can without a can toppling. And that's because the can has inertia. Okay, because when you look at the paper is light weighted. Okay, so it is difficult for um, since the can has more mass than the paper, so the can will have more inertia. Remember, I told you that more mass means more inertia. Okay, let's look at this other question. If you swing a stone overhead in a horizontal circle and the string breaks, the tendency of the stone is to follow. This pretty much something that you can try at home. Okay, take a stone, a very little stone or a very little ball, tie it to a rope, right, and swing it in a circle, right. Suddenly, if you suddenly allow the rope when it's in a state of swing, or if it breaks, if that string breaks, you realize that it is going to go in a straight line. That circle or that rope is going to go in a straight line path, or whatever you were trying to swing in a circle is going to go in a straight line path. And that's also because of inertia, right? You will stop swinging, but the ball or the stone will want to continue to swing. Okay, so these are examples of inertia. These are examples of inertia. If you put a coin on a paper, right, the coin drops into the glass when a force accelerates the card. So if a force accelerates the card, you see it drops downward. And so why do the downward motion and sudden stop of a hammer, right, handle tightens the hammer head? That's because if you look at this hammer head, it has mass, and more mass means more inertia. So when you hit it, right, remember this has weight. It has a tendency, that weight has a tendency to go down. So you have that weight acting down, and so when you hit, you have the weight and the force that you applied. It will help to tighten the hammer head. Why does a sudden downward yank break the bottom string, whereas a slow pull breaks the top string? Again, this is inertia. Okay, so we've talked about inertia several times. We've talked about inertia. And this example of you sitting in a car. So when you are sitting in a car and someone suddenly hits the brake, remember that the brake is stopping the car and not you. The brake is a force that is trying to stop the car that is moving. But since no force is trying to stop you, you will launch forward. And that can be very disastrous if you don't have a seatbelt. And so the reason why you are asked to put on a seatbelt is because when someone suddenly hits the brake stops the car. They want the seatbelt to be the force that will stop you. The seatbelt will exert the force that will stop you. So we want the brake to stop the car, we want the seatbelt to stop you. Because you and the car have the tendency to keep moving. You and the car, because you both have mass, you will have inertia. You both have inertia. And so if you don't have a seat belt and you hit the brake, you will launch forward. The car might stop because the brake is being applied on the car, but you will launch forward. So this is also an example of Newton's second law. We are going to look at that in a subsequent video because there is a force that is acting on the brake, but there's no force acting on you. When you flip a coin in a high-speed airplane, it behaves as if the airplane were at rest. The coin keeps up with you, and that is an example of inertia. If you've been in an airplane, try this. Can the bird drop down and catch the worm if the earth moves at 30 kilometers per second? Think about this. All right, so we are going to stop here. We stop here and in a subsequent video.